last time we did some stuff about stability of spinning bodies. This stuff's fun. This has been known since, like, this whole thing about flipping around the intermediate axis has been known for like hundreds of years, but it acquired a new name like in sort of last couple decades of the some Russian cosmonaut guy's name that I'm going to butcher if I try to pronounce it, like Zibakov or something like effect, which is it's the tennis racket flip effect, right? And yes, some cosmonaut did it on Mir and made a video, and then like they named it after him, even though it was known for like 300 years before that or whatever. Fun fact. And then we did like the numerical stuff, right? And this, yeah, so this we talked about kind of like the things you should do. So like if you're using a stock integration scheme, like if you're trying to use an ODE solver toolbox, like differential equations.jl, like on the homework, the move is to probably just use the Baumgart stabilization trick. If you can write your own integrator, then the RKMK stuff is kind of the move, and is kind of the better way to go. The hacky classic move is to just renormalize your quaternions in your RK4 step. But yeah, all of those are kind of, you know, passable. It turns out the normalizing the quaternion thing in your RK step is not actually that terrible. And it almost looks the same as, for the same reason as like this Baumgart stabilization thing only acts orthogonal to the true dynamics. It's sort of the same idea. Like it doesn't actually mess up the dynamics, and it's kind of okay. And you can like prove some things that basically you can show that it doesn't ruin the order of the Runge-Kutta method. So if you do RK4 and you just renormalize the quaternion, it turns out you still get a fourth order accurate like RK step, and it's sort of okay. So I don't know, fun fact. It seems sketchy. It's kind of sketchy, but it's okay. And that's pretty much what everyone does. Okay, so today we're going to talk about Newton-Euler dynamics, aka SE3. And so all the robotics people probably know about this a little bit. So this is the special Euclidean group, which is SO3 plus R3, right? Like it's rotation and translation in R3. And then we're going to talk about sort of practical stuff. So like quadrotors and airplanes, which are, say, like kind of maybe the canonical like SE3 systems in robotics that we see all the time. And there's a lot of fun stuff in there. So, okay. So I feel like probably everyone has done this before. Show of hands. No? Oh, wow. Okay, cool. Maybe this will be useful. So this is, again, yeah, like this is basically the full sort of like translation and rotation dynamics. For a rigid body. And basically you just mash up F equals ma for the translation stuff and the Euler equation for the rotation stuff that we saw last week. And just kind of stack these things. There's some subtlety though, which we will talk about. So you end up with something like this. You get your like mv dot in the n frame equals f in the n frame. And then you've got, you know, the Euler equation, which we're going to write in the body frame. So this is where the subtlety comes in. There's actually multiple ways to write this stuff down. So I will show you the two sort of common options. So yeah, the most important thing to like note here is that F equals ma always in an inertial frame, right? That's only valid in an inertial frame. Euler's equation is only ever valid in a body fixed frame. So that's why I'm writing little decorations on here, right? So the forces are in the end frame, the torques are in the body frame. And this is kind of subtle, and there's sort of some choices to make, right? So you will see both of these. And I think I made this hopefully point in omega dot. Yes, j omega dot. There's a dot on this guy. Thank you. So if I hopefully made this point in like the rotation stuff, like there's a million different sort of conventions for writing down rotations. You can write down, the attitude as body to inertial or inertial to body, and you could stack the quaternion up in different ways and all this stuff, right? Generally, the convention in aerospace and robotics is body to inertial, but that gets violated all the time. You'll see books where they do it the other way. Generally, the convention in physics is inertial to body is the other way. And I think this is sort of like this idea of, if you're a robot, you're sort of like living in the robot frame and you have all your sensors on the robot. So everything's body frame, right? By default. Whereas in physics, you're like in the lab frame looking down at the experiment. So all your sensors are in the lab frame, right? So they kind of do it the other way. Doesn't really matter, but you will see stupid, terrible things all over the place. Like one of the things that is absolutely mind-blowing is that in most of the books that do this, you'll find that they write the quaternion one way and the rotation matrix the other way. So they'll have like all the rotation matrices will be body to inertial, and then randomly they'll write the quaternions inertial to body. And then all the like transformations between rotation matrix and quaternion will be all screwed up, and like everything is terrible. So basically never, ever, ever trust like equations for this stuff that you get out of a book, or a paper. Like never trust them, because there's literally at least half a dozen conventions that are possible, and people mix and match them for no good reason, and it's absolutely just infuriating. So the message is, if you ever read a paper or a book that has anything involving rotations, quaternions, et cetera, SE3 dynamics, you pretty much need to sit there and like rederive the rotation kinematics yourself and like figure out what frames they're in, because people do just absolutely unbelievably dumb things with this stuff like all the time. It is kind of awful. So welcome to like, this is like when you graduate from like undergrad math and like no one knows what they're doing anymore, and there aren't any standards or like conventions that people reliably follow. So you basically have to do it yourself every time. Okay, so end of rant. There are some options here to put it mildly. So the two most common sort of things you'll see, again, you have to kind of be really careful because they won't tell you explicitly. You'll see the state vector sort of stacked up either of these ways. So you can have the first example, we'll do the one that like maybe, makes sense. You'll have like the position in the inertial frame. You'll have the quaternion, like sort of body to inertial, like we said. You'll have the velocity in the end frame, which seems kind of natural because F equals ma. And then you'll have the omega in the body frame, which is kind of natural because of Euler's equation, right? So just to be super clear about this, position, end frame, attitude, B to N, velocity, linear velocity, obviously, right? End frame. And then angular velocity in the B frame. Okay, so that's one option. The other common option is, let's see, let's do this. So mostly the same, except you write the velocity in the B frame as well. So you write all the velocities in the B frame, which seems a little weird. And what this is going to do now is you're now effectively writing F equals ma in a rotating frame. So you're going to pick up an extra term in there, and we'll like kind of. So this is all the same, except now this guy is in the B frame. So why would you ever do this? It seems more complicated and annoying to write the velocity in the rotating frame. You get a new term. You get a new weird Coriolis term in F equals ma, and you get a new weird kinematics to integrate VB into Rn, right? To account for the rotating frame. So why, does anyone have any clue why you would want to do this? Aren't they what? Aren't they yeah, so that's basically where this is coming from. So turns out the first one does not obey like a consistent group transformation for the whole state vector. The second one does. So the second one is actually SE3. The first one's not. And that's sort of practically useless, I have to say, but there's a bunch of fancy math that you can do with the second one that people are enamored with. Some of it's kind of cool, but honestly, practically speaking, I would say it makes almost no difference. There are fun control laws you can write down with the SE3 stuff, and you can like do all this nice thing with SE3 transformation matrices with that. The one thing that seems maybe vaguely useful about it is it turns out there's in the last like 5-10 years, there's been these French guys who've come out with a whole theory of Kalman filtering on Lie groups that's really nice actually, and you can prove for nonlinear systems, i.e. extended Kalman filters where you're doing a bunch of linearizing, it turns out if you write the Kalman filter down in the Lie algebra like this, for a Lie group system, you can prove convergence, like asymptotic convergence, exponential convergence of the nonlinear estimator of the Kalman filter by using a bunch of these group theory tricks. So that's the one thing that's kind of cool. Practically speaking, I think the performance of those things is like not much different from like just doing the first one, but the theory is very nice, and you can prove nice like global convergence results for these things. So kind of cool. Unclear if they're practically any better though, but like the math is nice. So that okay, so let's say for simulation, it really doesn't matter at all, I would say. But for control and estimation theory, if you're curious about this, it's called the invariant extended Kalman filter, and it's called it actually is cool. So what ends up happening, it turns out if you write the like EKF equations down in the Lie algebra, it turns out that the matrices associated with the EKF are invariant, i.e. they are not time varying anymore. Like, so a standard EKF, right, you have to relinearize everything at each step. Turns out if you magically do it in the Lie algebra like this and use the exponential tricks, it's invariant now. Like the A's and B's don't change because they're constant in that. What you're basically doing, right, if you think about it, the dynamics are sort of moving around on this sphere, right? Remember the quaternion kinematics? The invariant trick is you do it on the Lie algebra, which is always the tangent plane at the North Pole. So the North Pole tangent plane is constant, doesn't change. And you use the kinematics trick to like move the tangent plane around outside of the filter. So now the filter equations are always at the North Pole tangent plane, and so they stay constant, they're invariant, which is pretty slick actually, right? That's kind of cool. Okay, so any questions about that?
So a justification for using like body frame vectors that I've seen is like aerodynamics are in the body frame, and like your IMU or your accelerometer measurements are body frame. And so if you're like integrating those.
Yeah, so I would say that's so those things are all unequivocally true. Practically speaking, you're going to end up rotating stuff back and forth either way. And you go out and we'll do this in a minute. Like you're gonna but gravity's always in the inertial frame, right? Stuff like so you always have a mix and match situation where some things are inertial and some things are body, and you're rotating stuff. I don't think it makes a big difference when you're simulating, but there are nice things you can prove theoretically about the SE3 stuff. Like the invariant Kalman filter is probably the biggest example. Turns out controllers also generally work better with the second one. Empirically, like it is nicer for certain things, like writing down like PID in the second one works better, turns out, than the first one. Because in some sense it's the same argument, like that North Pole tangent plane sort of like doesn't move around as much, so it's like nicer to write things there because the things don't change as much. So like linear control works better there. Okay, cool. So here's sort of the key thing. So we're going to talk now about what's called the special Euclidean group. Everybody, so this is SE3, and it's the group of all rigid body transformations. And as we said, like kind of last time, all the useful groups are matrix groups. You can always write it down as a matrix. So here's what that looks like. So these are commonly written as big T for transformation, I guess. And so you'd imagine like this is kind of this body to inertial thing if we write the little decorations. And the sort of this big chunk up here is the rotation matrix. And then you have this over here, the translation vector. And then kind of just pad the matrix out like so. So we've got center of mass, translation, and then this guy's our usual rotation. And so if I can write, let's draw the cartoony picture, I guess. So if I have some like world frame here, so like N1, N2, N3, and I've got my rigid body over here. And this guy has a center of mass. So I've got like my body frame, attached to this guy, say. And I've got this, yeah, let's see, what else was I trying to say here? Oh, right. So I've got let's take some vector fixed in the body frame, right? So this might be a sensor measurement, right, that you're making, like might be your gyro measurement, whatever. Or it could be like maybe a better one would be like some camera, some vector to a feature from a camera, right, in a camera frame or that kind of thing. So you've got this guy over here. So we'll call this RB. And then what we want to get from this thing is Rn, which is the same vector that's pointing to the same feature, right? But it's rooted in the world frame and written in the other coordinate frame. So this is what this transformation matrix does. So we got this guy. Here's the translation thing. And we're going to multiply it by in the following way. So we take that RB, we pad it with a 1. That's just how you do it to make the algebra work out. And you'll get out QR plus D and a 1 on the bottom, right? So it rotates and then translates. Makes sense. And who's seen this before? Most of you guys? This is like KDC stuff, right? Like this is maybe kind of, yeah. Okay, so that's sort of the mechanics of doing it. Now what we're gonna do is look at the sort of like kinematics and velocity for this guy, right? And this should sort of make clear that whole state vector thing we just talked about before. Okay, so we're going to kind of do the following thing. So we're going to take a little sort of perturbation of one of these guys. So we got t times some delta t, right? So a small but finite transformation. And we're going to write down the kind of Taylor expansion-y stuff. So we got this guy, we got this guy. This is sort of the nominal t. And now we're going to write down a small, like a delta q and a delta d over here. And we're kind of multiply that out and sort of see what happens. So we're going to get obviously q times delta q. Then we're going to get over here q times delta d plus the original d. Okay, so this stuff over here is sort of obviously the same as what we had with SO3. So the fancy way of saying this is that SO3 is a subgroup of SE3, right? It's all there as usual. It's like this sub chunk. Okay, so now from this flow, we want to look carefully at this. So what is this saying about delta D? Specifically, maybe I should write the little decorations on here. What frame is delta D in? That's sort of the important takeaway from this. So this is, remember, this is N frame stuff. Okay, so this whole thing, this guy's in the N frame. So clearly to make things line up, like this whole thing has to be the N frame, right? Looking at this equation, like what frame is delta D in? It's in the body frame, right? Okay, so that's kind of the key insight. Is that when you're doing and you're chaining them together, so sort of what this tells you is like if I apply some little tiny delta d, to this guy, it ends up being in the body frame when I chain it together. So therefore, if I write down the velocity, aka Lie algebra here, just like with the rotation. So like this guy clearly is in body frame, right? That's like our omega hat thing kind of deal. This guy, the translation he got, and in the limit, if I take a limit here and make this a velocity, if I divide by a dt, basically, it says that my velocities are going to be in the body frame, which makes sense because the omegas are in the body frame and it's sort of consistent, right? But that's sort of where that comes from. So I'll do that now all the way out, I guess. So we get delta Q is approximate or equals, right? Like this is the exponential that we saw before. So it's our omega hat times some time step. And we can approximate this to first order with the Taylor expansion of the exponential as like h omega hat. It's first order in h, right? So we did that before. And then for delta D, we're just going to get, it's approximately, so this is in the body frame, right? So it's approximately just h times some velocity in the body frame, right? This is basically assuming like Euler integration or, tiny time step. So if I kind of write this out now, I'm going to get T prime is approximately, so my original thing, QD times I plus h omega hat for the small rotation, and then h times v in the B frame for the small translation, right? First order in h, and now I can kind of just pull this thing apart. And so if I multiply those together, I'm going to get q plus h q omega hat, right? Which looks just like, this looks familiar, right? So this is our rotation kinematics that we had before. And then over here, I'm going to get h q v in the body frame plus d in the end frame. 0, 1, blah, blah, blah. Cool. So that's multiplied together. Now I'm going to pull it apart and I'm going to get QD 0, 1, which is our original T, plus the first order in H stuff, which looks like QD 0, 1 times omega hat V in the body frame 0, 1. I guess I'll write the frames on. Okay, so what this looks like now is T, and then this is T, and then this guy is your like omega hat equivalent, right? So we'll write this as, I guess, W. Maybe we should write this as W hat. I don't know. Yeah, let's do W hat to be consistent with like the omega hat notation. So what you're doing now, right, is like, so obviously the kinematic equation is like this thing that's first order in H, right? That's like sort of your, so if I take the limit now, as H goes to 0, and what I'm really doing here is basically like, this is like a delta T, right? So I'm basically going to divide by H, right? So to make this perfectly clear, right, this is T prime equals T plus stuff times H. I'm going to go T prime minus T divided by H, right, which is the limit for T dot. Everyone get that? So let me write that down explicitly. So T prime minus T over H is going to be T dot, right? And that is the stuff that's left. So that's just T W hat. And that's my kinematics now, right? So we'll call this guy, like we have the hat map for SO3. We're going to call this now the hat map for SE3. And remember, big letters group, little letters algebra, right? So remember, Lie algebras are vector spaces. So this guy, I can stack up omega and V as a single 6 vector. And that's what my like SE3 guy is, right? And then when I had it, it means I stuff it into this matrix. How big is that matrix? 4x4, right? So this is 3x3, this is a 3x1. And then I pad it like this to make the algebra work out. Okay, so let's write that. So W equals, and again, you can do this either way, sort of arbitrary conventions, which you always have to be careful about, which is why you kind of have to do this stuff yourself and can't trust books and papers anymore. VB, we'll stack it like this. In R6 is the Lie algebra, SE3. And then, yeah, as a sort of as with SO3 for constant W, we have as so for constant W, this is a linear ODE, right? And so same deal as before, we can just exponentiate this guy, right? To get T of T equals T naught times the exponential of like TW hat, right? Exponential amount. I'm gonna go with that. Again, linear systems, right? Think about it as E dot equals E omega hat kind of thing. Oh, the other kind of note, right? Remember for linear systems, we usually have like A phi, right? And here it's phi A backwards. Why is that? I don't know. So what if I flip the order? Like what happens? I get the wrong answer because matrices don't commute, right? But like, does anyone have any thoughts on what's going on there? Like what happens if I flip the order? Like what would be happening? Yeah. Opposite direction, yeah. So here's a way to think about this. This guy's in the body frame, and this is body to inertial. What happens if I flip the order and I put the W hat on the other side? It means you're writing the velocities in the inertial frame. So you can do that. So, but what that corresponds to, if you do this the other way, it corresponds to having all the velocities in the inertial frame. So if you were to write down omega in the inertial frame instead of the body frame, and in this case, V in the inertial frame, you would end up with the kinematics the other way. And that's why, and you will see that in books. And that's what's going on in the linear systems case. It's effectively like inertial frame velocities. Is sort of the difference. That makes sense. This is why, again, you got to be super careful with this stuff. You'll see like multiple conventions. You'll see mix and match. So the one thing that is clear, it's still a group if you write them both in the inertial frame. It just has everything flipped, basically. It's not a group if you mix and match. So if you write like omega in the body frame and V in the end frame, it doesn't form a group. You can't end up writing it nicely as a single matrix transformation like this. It's sort of inconsistent, right? Okay, any questions about this? The same kind of gymnastics we went through for the just rotation case, but it turns out, right, you can stuff the velocity in there and come up with as long as you write it in the body frame and everything's consistent, you can write this whole thing as a group too. It turns out like fun recent-ish research about last 5 years stuff. I mentioned this invariant Kalman filter stuff. It turns out you can stuff lots of other things into a matrix like this and keep going and make bigger and bigger groups. And some guys at Michigan had a field day with this recently and like came out with a bunch of really, really nice results for invariant filtering for legged robots. So it turns out you can like write down the foot position in the body frame in there as like a new vector, and it still obeys the group transformation properties. You can start writing down like sensor biases, like your gyro bias in the body frame. You can sort of stuff in there too. So all these like new things, you can kind of like keep stuffing into this group and make a bigger and bigger matrix. And it still maintains this group symmetry property. So you can write down invariant Kalman filters for like some pretty interesting things. So cool stuff, useful in robotics. You get out provable exponential convergence for your nonlinear system in your extended Kalman filter, which is slick. So if you can stuff it into a group and show that it's a group, you can automatically plug into like a pretty large body of work on invariant filtering for state estimation. And there's lots of control literature on this kind of stuff too, where you can exploit this structure to get like invariant control laws that are sort of written in that tangent plane that don't have to change as you move around, which is cool. Okay, I'll get on that stuff. Yeah, so SE3 super common. You'll see other things too. Like basically it's become fashionable to like invent new groups for various robot applications where you stuff various sensors in there, various kinematic parameters of the robot, and show that it all obeys a group property. And then you can do like fun filtering things and whatever on it. Okay, cool. So we'll do now the full Newton-Euler dynamics. On SE3. So this is, again, we're going to do with the V in the body frame, which sort of, you pick up some extra weird terms. So let's make sure everyone's on the same page with that. So X dot is going to be R dot and N, Q dot, which is our usual stuff, then V dot in the body frame, and omega dot in the body frame. So the only weird thing here is really the velocity in the body frame. Everything else is kind of normal. So let's write that out. So the first line, remember, our state has V in the body frame, so we've got to rotate that with our quaternion to be in the inertial frame. So I'm going to write it like this, just with a rotation matrix, because it's quick and easy, but you know what to do there from last time. So that's pretty straightforward. Quaternion stuff we know from before, so I'll just quote that. This is sort of our left-hand quaternion multiply, our like hat matrix, and then like our omega in the body frame. So we did this last time. Cool with that. This, by the way, that whole L and R and H notation, that is our special made up in my lab notation. It's starting to catch on. There's some other papers that do it, but like we kind of made this up, so you may not see this too many other places. Just FYI, I think it's the cleanest way to do it, obviously, because whatever, it's our own brand, but just FYI. Okay, so then here's the weird part, right? So this is F equals ma in the body frame. So we're going to write the forces in the body frame, and I guess I'll just write this down and I'll show you how to get it. You're going to pick up an extra like Coriolis term associated with the rotating frame, and that looks like this. Again, we'll write it out in detail to show you how to get it. And then the last line is just standard Euler equation, just kind of solved for omega. So we take everything to the right-hand side and invert J. Remember, yeah, the inertia is always in the body frame. That's okay. So now how did I get that? So this is clear. The top line is clear, right? I just literally rotate V in the B frame into B in the N frame, and then it just, usual integration. This one's a little strange. So let's write this one out in detail. Okay, so the way this works is, all right, so I'm going to write down V in the N frame equals Q times V in the B frame. That's super clear. That's the top line. Now I'm going to differentiate this with respect to time on both sides. So I'm going to get V dot N equals Q dot VB plus Q V dot B. Cool. So far, so good. Now I'm going to plug in the kinematics for Q dot, which is that Q omega hat guy. So I get Q omega hat B frame, V B frame, plus Q V dot in the B frame. Cool. And the last thing to remember is this is, so this V dot, this is A in the inertial frame. So F equals ma in the inertial frame, right? So I'm now going to write down, this whole thing equals 1 over m times F in the N frame. So I just wrote down F equals ma, and then I went through all those gymnastics to like sort of write it in the body frame, and I picked up that extra term, right? So this whole thing tells me now, if I want to write the whole thing in the body frame, I'm just going to solve this, just going to massage that around and solve it for V dot in the B frame. This is the guy I want, right? So I'm basically going to like sort of move the Q's over and whatever. Cool. So here's V dot in the B frame equals 1 over m Q transpose, because that's Q inverse, F in the N frame minus omega cross V. Cool. Everyone see what I did? So I just took the Q's and multiplied through by Q transpose. Now the last trick is, what's this guy? So this is F in the N frame times Q transpose. So Q is body to inertial, Q transpose is inertial to body. So this whole thing is just the F's in the body frame. instead of the inertial frame now, right? So now we get the result we were after. So there you go. So that's where that like third line comes from, which is the F equals ma stuff. Okay, so this is SE3 dynamics. The SE3 part is really the top two lines, right? The kinematic stuff. The dynamics part, I guess, is also, but it's basically that stuff is like writing down F equals ma in the body frame, which gets you this extra term, and then Euler's equation, which we already had in the body frame, right? To be consistent with the velocities being in the body frame. Sort of just for completeness, because you'll see it a lot because it's super common. If you don't do it the SE3 way, it's sort of easier. This is the stuff you're probably familiar with more, right? Would just be standard F equals ma. So you'd end up with like x dot equals r dot n, q dot v dot n omega dot d. And this would just be, you know, v, same quaternion kinematics. This is now just F equals ma, normal F equals ma in the end frame, and this is the same Euler equation stuff in the body frame. All right, I think that's okay. So basically, this is the recipe, and now if you want to simulate any rigid body system you want, airplane, quadrotor, legged robots are often done this way for weird reasons. I don't know, take your pick. There's probably other ones, underwater stuff, space stuff, spacecraft. Basically, now all you need to do is compute F and tau. That's it, right? All the rest is there for you. And now you can do like any rigid body robot. So this is actually super, super useful. Okay, so let's write down like a couple of the most sort of canonical, popular rigid body robots. Quadrotors. These are ubiquitous, right? Everyone's seeing these things. So if you ever need to simulate one, I mean, there are simulators, but you know, if you want to write your own controller, et cetera, you probably want to be able to do this. So let's write one down. Again, there's like multiple conventions for everything. So always be super careful. So we're going to have like a center mass sort of in the middle of this guy. We're going to have the four propellers coming off like so. Let's see, what do we have here? We've got, so I guess we'll make the propellers rotate sort of like this. So there's a key sort of, they do not all rotate the same way, right? So you get opposite torque, so the thing can sort of cancel out the prop torques. And then we're going to have mass M, inertia J for the whole thing. And then we'll call these little vectors from the CG to each propeller SI. And this will be in the body frame, I guess. All depends. So these guys, so you'll have four S's. So this accounts for whatever the vector is. So it'll be super generic. Let's see, each prop exerts a force which is thrust in the B3 direction, right? So if we pick a sane coordinate system where the z-axis of the body frame is up, like unless you're a weirdo, that's probably what you would do. So we'll go with that. And then so you get a thrust in that up direction in this frame, out of the page. And then you get a torque also about that, a prop torque. Does anyone know why you get prop torque? Like, what is that? How to think about that? So you get thrust, obviously, that's what you're trying to do with the propeller, right? Why do we get a torque? Yeah, so, but where's it come from? No, well, sort of, yeah. So what it's actually coming from, right, is the way to think about this is each propeller blade is actually a little wing, right? So the wing generates lift and drag. The lift is your thrust, right? The drag on the propeller blade ends up being your torque, right? Does that make sense? So it's literally I'm getting drag and it's spinning around. The drag force is sort of acting against the motion of the prop. And as I sort of integrate that around a rotation, I get a torque. Clear? So yeah, literally propellers are just little wings. And that's the way to think about them. They're little airfoils. This is also why they twist, by the way. You notice propellers are never like straight. They always have this like twist to them. It's because the velocity, the wind velocity over the propeller changes as you go out from the root to the tip, right? The tip, it's moving faster, and inboard, it's moving slower. So you actually want to vary the angle of attack as you go out, right? Because the airflow is different speeds. Anyway, that's a whole other thing. So you get torque in the sort of plus or minus B3 direction. Due to drag. Okay, so you get, so if I write down all the forces, I got Fi equals KT times U. So this is sort of typical. There's more complicated versions of this that account for more stuff, but basically sort of like to first order, this is called the thrust coefficient. And if this is times, your input, you assuming that's like some motor current or whatever command, this is typically how it works out to first order. Again, more complicated stuff. And then your torque is going to be this is called the moment coefficient times, again, your UI. And these are actually specs on the propeller. So for a given prop, you can either go do wind tunnel experiments to figure this out, like basically put it on a test stand with a load cell and free stream and like measure this stuff and fit a line to it. Or you can generally, for most anything that's like above the crappiest hoppy grade stuff, you can actually find that these coefficients advertised for props typically. Anything above a certain price range, the manufacturer will tell you these. Yeah. So we're gonna, yeah. So this is where it gets more complicated. So this is assuming basically, yeah, that you get like instantaneous, like that yeah, it's essentially like zero inertia, that it like spins up instantly when you apply torque to it like this. A more complicated model, you would account for motor effects, prop inertia effects, and what that ends up doing is you basically add states for these things, right? So in practice, like this is really proportional to like omega squared. So you would write that down, and then this would be like a torque, and you'd have like Newton-Euler dynamics, for the props, and you'd account for airflow over the prop in the sort of like horizontal plane, right? Which is going to impact this, because now basically if I'm moving this way and my prop's doing this, I've got more airflow over this side than the receiving blade, right? So this is actually this is what sets the speed limit for helicopters. The fastest helicopters in the world top out a little over 200 miles an hour. And it's because basically what ends up happening is the receding blade ends up installed because the forward velocity is almost what matches the receding prop velocity. So that's bad. So you end up getting torques because of that, right? So all kinds of bad, weird stuff happens with rotorcraft. It gets a lot more complicated. This is like a good model near hovered. And this is what most of the quadrotor control stacks do. You can get more complicated for sure, and higher end quadrotor controllers will do some of this modeling, like you're saying, accounting for prop inertia and more of these aero effects. But the standard like baseline model that you can use, like if you were just if I just needed to get a quadrotor to fly around in the lab, like this is where I would start. If I wanted to get like uber accurate tracking performance and like super aggressive maneuvering, I'd probably start doing some of the stuff you just mentioned, right? But this is kind of a good starting place. Okay, cool. Any other questions about this? Aerodynamics is hard. but we don't have to do too much of it. It turns out to fly quadrotor. Okay, so since f and tau are linear in U, and U, remember, is 4-dimensional. I got 4 propellers. We can write this as a matrix. So we're going to get something like essentially F in the body frame is equal to some 3x4 matrix times, so I guess I gave away some stuff there. So I've got my 4 motor commands. And yeah, this actually varies a lot, right? Because you've also got a motor controller in the mix here, right? When I send these commands to my ESC or whatever, so there's complicated stuff in there too that we're going to ignore. We're essentially going to say, I'm assuming my motor controller, my low-level motor controller is good and it's fast. And the dynamics associated with the motor controller, like ramping up, are much faster than the dynamics of the quadrotor itself. And that's kind of at the heart of ignoring a lot of these things, like you said, like prop inertia effects. Okay, so remember, the thrust is always in the B3 direction, and it just adds. So we just get this kind of thing for force, simple enough. And then we got to get gravity in there. So we get a Q transpose times m, minus mg kind of thing. And yeah, because remember, that's in the minus z direction in the body frame, or in the inertial frame, right? So I have to rotate it. Okay, and then we've got to get the torques. So we get both this prop torque in the z direction from drag on the propeller blades, and we also get this cross product term because the prop is offset from the center of mass, right, by these s's. So we're going to get like an s cross f thing. Okay, so torque in the body frame is going to be, first we get a very similar thing to what we just had up there, where each prop has a drag torque, and these are going to flip signs. This is where you have to be careful and like actually pay attention to your particular quadrotor and your choice of reference frame for the body frame. But basically, you make every other one spin the opposite direction so that they cancel out, so that you can hover without sort of getting a net torque, right? That's sort of the magic quadrotor trick. Look at that. Then we're going to get these. So that's the torque, again, the drag torque on the propeller blades. Then this term, so like sum over I, SI in the B frame cross each individual thrust, right? So this KT times UI kind of guy. And basically right now we're assuming, you can simplify this some more, which is common. So usually you write down the body frame to align with, usually these things are symmetric and you write down the body frame so it aligns up with the propeller blade axes or something, in which case this gets even simpler. And we'll do you can get this down to be like this sort of thing. So like be like S00. Something like this, right? And where this guy is norm of, the SI. And then you get this to look like one big matrix So it's something like this. Cool. Now you're good to go. Now you just plug all this into the Newton-Euler stuff. Okay. Yeah.
S1 equals like S, are those the same as?
These are the norms of the S's. So like those little S vectors are like, this is, I'm assuming that I'm assuming A, that the quadrotor is symmetric, and B, that I line my body frame up with the prop axes, right? So that each prop is just in like the X or Y body direction. So like one in the plus X, one in the minus X, one in the plus Y, one in the minus Y. So then like each of these S's just looks like that, right?
I mean, like, is S in that S1 vector the same as S in S2?
Oh yeah, I mean, not necessarily. So I should probably number those. I guess we'll do this. S1, S2, S3, S4. So, but probably these are all the same, or at least two of them are the same and the other two are the same, that kind of thing, right? Based on what your quadrotor looks like. This is pretty normal, I guess that's what I'm saying. You'll probably see something like this. You'll see some like input Jacobian thing with a bunch of like prop coefficients and these lengths associated with the prop motor offset from the CG, and it'll just look like that. And it's like basically linear in the control inputs to first order. Okay, so what did we kind of talked about this. What is not missing from this model? Like, where does this break, basically? Thoughts?
Airflow.
Airflow, specifically, like this does model the prop stuff, right? This model is like propeller thrust and drag, right? Like, but it's missing any kind of aerodynamics associated with the body of the quadrotor, and it's missing more complicated airflow that happens when you have a non-zero free stream. Basically, like if I'm moving horizontally and I have some ambient wind sort of blowing over the prop the other way, that messes with this, right? That, like we said, that induces a torque due to like the leading edge going faster than the trailing edge and stuff like this. So all kinds of bad stuff happens, right? So we ignored a lot of aerodynamics. Turns out you don't need them. So the other kind of fun thing, right, is aerodynamic stuff is all proportional to V squared, right? Everyone knows this, right? So, so to first order, it drops out. So if I'm near hover, if I'm not moving very fast or I'm like linearizing about hover, this is what happens, right? Only the prop stuff actually matters. And it's all proportional like omega squared on the props. And then all the airflow stuff, you know, past there, it's all proportional to V squared. So it all drops out for small velocities. But if I start to move fast, then it starts to matter, right? So if you're doing like crazy aerobatic stuff, you know, so body drag, wake and boundary effects are another big one. So has anyone ever tried flying a quadrotor near the floor? This actually came up in our seminar talk on Friday. So you get like what's called ground effect or just boundary effects. Basically, you get this like cushion effect from the air, like basically bouncing off the floor if you're close to the floor, and that actually increases your lift. So so that's kind of interesting. Same thing with flying your walls. You get weird boundary effects. So it turns out with a quadrotor, for this model to hold, you actually have to be, you know, a meter-ish away from the floor. Say you have to be up high enough. So in particular, this stuff starts to like be a poor model when you go to land. You actually get way more lift than the model predicts when you get close to the floor. Let's see. These start to matter. Go fast and/or fly near walls, floor, etc. So this is kind of where people are into like, so yeah, if you start going fast and doing aggressive things, more aero stuff starts to matter, flying near walls, etc. So this is kind of where people are into machine learning, like data-driven modeling of these things. There's a few labs that have done a lot of work, both on constructing, doing like residual learning, basically, to like learn these extra dynamics terms from experimental data to try to do better prediction. So there's a lab, Davide Scaramuza's lab in Switzerland has done a ton of work on this last few years, and they've got like really ridiculously impressive models now that they've collected tons of data sets in a big mocap arena, and they can fly this thing. They can do insane aerobatics and track to like a few millimeters worth of accuracy over, like tens of meters at like insanely full gas, speeds, which is awesome. And there's also been a lot of work on just direct policy learning, right? Where you're not trying to build a predictive model, you're just trying to make the controller better. And roughly speaking, our seminar speaker, Sunjo from Caltech, who's here Friday, their lab's doing stuff like that, where they're learning like sort of controller terms directly, like just doing policy stuff. Their particular brand is heavily, biased towards giving nice control theoretic guarantees on performance, but they have specifically some really nice work on landing. So they call it neural lander. So you can like basically account for all this ground effect stuff and do like super fine control, like near ground effect obstacles and stuff like this. They have a pretty slick demo where they fly over a table, where without their sort of learned stuff, that it does this over the table because of the ground effect. And theirs just is like rock solid straight over the table because it accounts for that effect, right? So kind of cool. Okay, any questions about this stuff? Okay, so then in our last 10 minutes, we will do a crash course on how airplanes work after our crash course on how quadrotors work. Because, this happens. People do drones and stuff are important, right? Okay, so let's talk about airplanes. So I will draw a terrible cartoon airplane, as all my drawings are terrible. I mean, not just the airplane, they're all bad. Okay, so we got wings. We got horizontal tail. This is kind of the canonical airplane. There are different versions of this, obviously, right? And we got our vertical tail. Okay, so control surfaces on an airplane. And we got a CG somewhere over here, probably. Actually, it should be a little forward. That's probably it's close enough. Does anyone know where it should be? Any aero guys in here? Where's the center lift? That's the question, right? Does anyone know? It's at the quarter chord of the wing. So it's a quarter of the way back from the wing end of the wing, turns out, is where the center lift is, usually. Modulo, lots of approximations, right? But so this is kind of wrong. It should be up a little bit more. And then we got, like, let's say our propeller up here. Okay, so control surfaces. We got ones on the wing here. These are little flaps that I can actuate, right? What are those ones called? Ailerons, right? So those are for controlling roll. You actuate them together, where one goes up and the opposite one goes down, right, to get a torque. And then I got ones on the horizontal stabilizer back here that work together. So these guys move up and down together to actuate pitch, right? What are those ones called? Elevators. And then I got one on the vertical tail back here that I can use to do yaw. And that one, what's that one called? Rudder. Cool. And then obviously I have my propeller. So the standard sort of set of control inputs for an airplane. So our U is throttle, which is, related to thrust. It might be like, a derivative of thrust or whatever. Then I got my ailerons, elevator, rudder. And sometimes these are combined in weirder designs, but this is kind of your canonical tube and wing airplane design. And this is, again, a 4 vector. So 4 inputs, just actually same number of inputs, right, as the quadrotor. And then, so we're going to basically use the same sort of propeller model as the quadrotor. So this is a fun question. So this prop has torque just like the quadrotor, right? So this airplane always has a torque coming from the prop that's like trying to roll the airplane, right? So has anyone experienced this before? It's very weird stuff. Has anyone fly a small airplane? This thing called P factor that like is related to this. So it turns out when they build small single engine airplanes, they actually build into the airframe, they trim the airframe out at the factory so that at cruise, it's at equilibrium. Like they cancel out the prop torque at cruise. Like that's baked into the airframe, which is kind of wild. So it's like the airframe's slightly biased and twisted to sort of like all the lifting surfaces have that baked in to like cancel out the prop torque at cruise. Cool. So here's, we're going to get into this whole lift drag thing. So each lifting surface, so like propeller blades, all the wings, vertical, horizontal, etc. Generate lift and drag. So here's how lift and drag works. All right, so we're going to take a side view of an airfoil, aka wing. So we've got the sort of what's typically written as V infinity, which is the free stream airflow. So like if you went far away from the airplane and you just had like wind, right? Whatever that is. So I guess let's call this V air. But yeah, you'll see it is written as V infinity typically in the aero literature. We're going to have our airfoil shape, which again, apologies for bad drawing, and I will exaggerate this a lot. So here's our curvy airfoil thing. So here's some line associated with like the free stream airflow. This angle between the free stream airflow and the wing, does anyone know that's called? Angle of attack, right? So that's written as alpha. And then, so that's the angle between the free stream oncoming airflow and the lifting surface, the wing. And it's written in, and we then decompose the forces, the aerodynamic forces on the wing into two components that we call lift and drag. And like this F may be, you know, something like, it's probably something like this roughly, right? It's some 2D vector, right? And we're going to just decide to write it in these two components, L and D. And the specific thing to keep in mind is that this lift and drag frame, it's called the aero frame. It's associated with the free stream direction. It's not associated with the wing or the airplane. It's the frame, it's the wind frame is what we're doing, is where we're decomposing this into, right? So that messes people up all the time. And it's all coordinate transformations. So basically what we have to do, right, is we take our airplane stuff, we rotate into the wind frame to compute lift and drag forces, and we rotate that force vector back from the wind frame into the body frame to like tack it onto our dynamics. Okay, so what do lift and drag curves look like? I talked too much today, so we're sort of running out of time. See how far we get. We might have to do this next time a little bit. Okay, so here's L versus alpha. And so roughly it's linear-ish in some region near zero. And so we pretty much always approximate this as linear, as all things. And then it starts to do this. Once you get to a certain point, it starts to taper off. So it does something like this. It roughly looks like a sigmoid. And then it sort of tails back down. Sort of does this. And this is a bad drawing as usual for me. So something like this, sort of sigmoidy, and then like sort of, yeah. And so this linear regime, say, you know, here-ish, right? This is typically where we like our airplanes to live. We don't like going outside of this linear regime. And usually this is, for most airfoils, this is sort of like plus minus 10 degrees. Okay, so question is, what do I call the peak over here, where this thing sort of rounds off and starts to go down? And this is a bad drawing. Maybe I'll fix this up slightly. Anyone know what that's called? That's stall. Yeah, so when you talk about stall in an airplane, it's the peak of the lift curve where the lift starts to decrease now. So if I'm doing this, I'm getting more and more lift. At a certain point, the lift actually goes the other way and I start to do, yeah. Okay, so this peak here is stall. And we don't like to go there. Going there is bad. This is where, and it's in practice, this is due to flow separations. Basically, the airflow is starting to separate off the trailing edge of the wing. You get detached flow and you get turbulence coming off the back of the wing. And you feel this in the airplane as buffeting. You start to shake and it's bad. You don't like this. Okay, and then drag. So same thing, alpha, and then D here. Drag is roughly quadratic for small angles, and you've got a certain amount at zero angle of attack that's due to like skin drag, just whatever friction. And then as you increase the angle of attack, roughly speaking, it increases quadratically. So. And let's see. Yeah. Is everyone good for like 2 or 3 more minutes? We're almost done with this whole thing. So I don't want to like keep you guys if you got to go. But yeah, so generally speaking, what you do is for most applications, meaning like if you're designing a controller and you don't want to do insane aerobatics, you use linear and or quadratic approximations of these. Let's see. Okay, so like something like L is approximately so the total force looks like this. I'll write this down. We'll talk about what all these things are. CL naught. Okay, so this is lift. This is the density of the air. This is the area, the wing area. This is velocity squared. This guy over here, CL naught, this is called the lift coefficient. And this is actually the slope of this lift curve at the origin, right? And then this is the angle of attack, which we already know. And then the other one we get is drag. So this has the same form, rho A V squared. And then it's going to look like CD naught, which is the height of that lift curve at the origin, right? So that's a constant term. And then maybe a lot of people leave this out, right? So if you're linearizing, this goes away, but then maybe you'll get what would be called like CD2 alpha squared. And then this guy's called the drag coefficient. So you hear about drag coefficient for all kinds of things, cars, et cetera, right? That's what that is. It's the constant term from the second order Taylor expansion of the drag curve as a function of alpha. It's like how far off it's the amount of drag you get at zero angle of attack, right? Okay, what else is there to say about this? So the way you model, so we talked about control surfaces, ailerons, elevators, rudders. The way you model those, the generic name for those is a flap. They're all called flaps. And what they do is just change the effective angle of attack when you change those control surfaces. So here's how you model that. So you got alpha effective equals alpha plus this epsilon I times ui. This so this would be your control input. So this would be like your flap angle. flap deflection angle for, elevator, whatever rudder. This guy is called your flap effectiveness. And again, this is like wind tunnel model, whatever. And that's it. And then you plug everything in and you get your forces and torques and you get your, just add everything up. We're not going to do this by hand because it's complicated. As you can imagine, there's like center of lift for every single one of these and an offset vector and lots of cross producty things and whatever. This model is, this is literally how you simulate like a commercial airliner, small plane, like all that stuff, most fixed wing drones. This is like the standard thing. This breaks when you start to do crazy aerobatics, basically high angle of attack, right? It's what we assumed plus minus 10 degree-ish angle of attack. When you start to do crazy post-stall stuff, this starts to break. So aerobatics, really aggressive aerobatics, or perching is like another one where you try to like a bird perching. People have done this in robotics. It's kind of fun. It's actually a really fun robotics problem. But yeah, that also breaks this model. The other thing that we didn't talk about that's important is prop wash. Which is the sort of like induced airflow velocity from the propeller over the lifting surfaces. So like anything downstream of the prop is going to have a different speed of airflow than the free stream speed due to the propeller. So if you have a propeller, you got to worry about that. Cool. Okay, so that's kind of the whole thing. Just as a parting sort of thing about rigid body dynamics, other common single rigid body systems that you will encounter probably in robotics would include, underwater stuff, super common spacecraft, wheeled vehicles and cars are also, you got this stuff going on. And actually legged robots are also super commonly modeled using what are called centroidal dynamics, which is where you assume all the limbs are massless and just model the center of mass sort of rigid body dynamics, and looks like this also. So most of the legged robot controllers also have these dynamics in them. Okay, that's it for today. Sorry for going over. See you guys next time.